All right. Hi, everyone. Let's get started. A couple of announcements. One, your homework 2 was due yesterday. If you still have late days, you can still work on it, but officially it was due yesterday. Your homework 3 will go out on... Could be Thursday night. As soon as Thursday night, maybe even sooner.
It's ready to release. I can release it whenever.
Oh, who wants it now? It'll go out soon, and we'll be due in 2 weeks. But what will be due before that is your project proposals. So March 2nd, which is, let's see, Monday, your project proposals are due. We will post a little bit of information on Piazza. We'll also give some example project topics, maybe in lecture today if there's time. If there's no time, we'll just post them. And the format is you submit a Google Doc with a project proposal. We will look at that during the coming week between the 2nd and a few days after it, give feedback, discuss with you in the Google Doc such that within a week after your initial submission, we should have converged together on something that is agreed upon to be a good final project plan and topic. Any questions about logistics? Olivia? Are you allowed to pivot? Sure, but I mean, let us know. And the intent of the proposal is that we get to something that you know we are excited about. So if you pivot later, there's less guarantee we're excited about it. So yes, it's allowed, but then you lose the guarantee that we are excited about what you're doing. Okay, cool. Let's get started for today with technical topics. Aravind will kick off the first half, covering more GANs.
Okay. So we finished the previous class based on the finishing with all these big GAN deep, big GAN, and style GAN architectures. So not much has changed after the big GAN deep and style GAN as far as image quality goes. So the main thing that I wanted to do in the next part is to show you the various applications that all these progresses in GANs have enabled, like in terms of image, in terms of graphics and like various other domains, as well as show you a small update to style GAN v2. So the same authors who built style GAN came up with a version 2 of the model, which is basically something you would only want to work on if you looked at all the images in like a lot of detail. So for instance, if you look at the first image over here, like it feels normal to you, but if you actually look at the activations prior to the generated image, they observe these this particular phenomenon called water droplets, or water droplet-like artifacts in the activations that are building up all the way up to the generated image. So that ends up creating these weird artifacts in the final generated image that they've already circled in the as red circles in the image. So it looks fine to us, but you know you want to be as photorealistic as possible. Yeah.
We posted some updated slides also, just 1 minute ago on Piazza. So if you want the slides that have all this, re-download.
Okay. Okay, so this is something that you wouldn't particularly care about as a machine learning person, but as an art, like someone interested in graphics or graphics applications, art, etc. These are pretty important. So how did the style GAN authors actually end up addressing this? So to those of you who felt that the adaptive instance normalization was pretty ad hoc and complicated, this fix is actually a little more ad hoc than that. But it has a few nice insights, and you just need to know the high level. So basically, this was the original style GAN, where these style vectors are being propagated into the generator at various levels. And those style vectors are actually coming from your latent variable that's been passed forward through an MLP. So the figure in the second column has the more detailed version of that, where you're basically getting your feature map, and you're calculating the normalized. You're calculating the first order statistics per channel, and then you're basically modulating the statistics with these learned style vectors, and a convolution works on top of that. So what they basically did in the revised architecture, the version 2, is that they would rather just have the modulating the standard deviation, and they wouldn't actually modulate the mean. So basically, this means that the style vectors are just going to scale the per channel statistics, and the biases are just going to be handled by a separate vector that's added outside the style adjustment. So the gray box is basically what's the style adjustment that's being made using your style vectors. So earlier, the style vectors were also adding a particular adaptive offset, but now they're just not doing that. Now it's just going to be used for scaling. So that means that the scale version can be just clubbed into the convolution, and you don't really have to worry about having an actual instance normalization layer, because the scale is just a way to initialize your convolution to match the particular activations that you desire. So basically what's going to happen is your convolutional kernels that are actually building in each style layer, they're going to be modulated by your style vectors that are coming in at every level. And so this is what the authors refer to as weight demodulation. It's just basically performing this kind of style-based changes to your generator through the weights of your convolutional kernels, rather than explicitly doing an instance normalization. So this allows them to solve this issue of water droplets. And so they actually have a video. So it seems like the videos won't play.
Yeah, videos won't play.
Okay, I guess I can just go to YouTube. So let's watch the video. So these are the blob or droplet-shaped artifacts that the authors seem to care about particularly. So you can notice how they're pointing it out at various levels. So one way to think about it from a machine learning perspective, why is this important? If you want to have a model that, like if you're training a deep fakes detector model, and it may be easy to just figure out which is a GAN generated and which is an original image based on these droplet-like artifacts. So you can think of this as basically trying to address the problem. Whether it's worth doing that or not is questionable. But so you can see that they basically observe this problem by focusing on the activations of the generator rather than the final image. It must be really hard for you to notice this problem in the final image, but if you look at all the activation feature maps, it's pretty clear that there are all these gaping droplet artifacts across. And they also point out various other artifacts, like the phase artifacts, which prefer certain specific aspects of the image. And these are all the baseline versions that they've observed across various different images. So I'm not sure how many of you find the version 2 more realistic or something like that, or even better. It's really hard to discern the quality. But that said, I think they have actually also done lots of other interesting experiments. Like source and like target mixing with using the latent vectors, which I guess you had access to that in the previous class, like you saw that, but it seems to me like this looks even better, or at least, yeah, it looks more photorealistic than the previous version. So one nice thing about using this kind of an architecture is once you have all these various levels or resolutions of feature vectors that are using, you can then take a target image and figure out what its latent is. And you can perturb the latents. And you can see all these kinds of cool three-dimensional shearing that you can do with these models. And so basically, you're iterating over what is the right latent, and then you're perturbing it in all directions. You can see it learns notions of color, the pose, it can actually rotate the car, elongate it. These are all concepts it's basically learned just by generating the data set, and there's no geometric information that's been provided during training. All right. So that's it for StyleGAN version 2. And you can basically the TLDR is if you want a really high quality image generator with structured latents at various levels of resolution, you should use a StyleGAN. And if you want to have a really good class conditional image generator that works at scale, you should use a big GAN. And everything else is sort of irrelevant now because it's like these are working so well that it's really hard to beat their quality. And all these pre-trained models have been made available by all these different papers. So you can, and there are like so many people, so many artists who just basically take these pre-trained models and play around with it, like try it on a new data set by fine-tuning it, and so forth. And all those applications are really cool. So one thing that we want to talk about is this somewhat orthogonal idea, but it's pretty interesting, on information bottlenecks and how to use them in combination with GANs. So think about a GAN that just operates with a latent variable model. So imagine that instead of feeding the actual image to your discriminator, you feed in a latent variable. And you do this for both the generated data and the actual real data. So there is some encoder that takes in the generated data and your actual real data set and puts it into some latent space. So now the discriminator is just going to take in the z that you get from this encoder. And so how would why would that make sense, and how would such a model look like? So the discriminator is now going to classify in a much lower dimensional space. So it's possible that if these latents are only capturing the high-level entities of the image, then it's unlikely that for the discriminator to focus on spurious things and cheat. And that way, the GAN optimization could become much better. So that's the high-level motivation. But you want to make sure that these latents are good then, right? You want to make sure that these latents don't, basically, they don't take everything that's there in the image and put it into the latent space. You want to make sure that the latent space is somewhat crippled and has incentive to lose a lot of the high-frequency information that's contained in the original image. So there is this notion of information bottleneck. So one way to think of bottleneck is you just think about it in the autoencoder structure, where you take in a big image and then you're putting into a smaller latent space, and then you're basically generating your image again, which is what happens in an autoencoder. So people call it bottleneck because it looks like a bottleneck. But then what is variational here? So when you actually bring in information theoretic quantities and say that, oh, I want to make sure that the latent variable doesn't contain all the information that's contained in your original input, then you want to make sure that the mutual information between the original input and the latent variable can only be up to a certain limit. And you say that it's going to be less than or equal to some IC, which is some threshold that you say this is the number of bits that can be shared between the latents and the actual image. So enforcing this constraint is referred to as a variational information bottleneck. The variational is because this particular term is not tractable. So you come up with a variational lower bound to this, and then you try to use that as a constraint to your latent variable model. So this is the constraint that we are interested in. And there is a paper called the Variational Information Bottleneck by Alimi et al. That actually proposes a way to enforce this constraint using stochastic gradient descent by writing this term as like having an expectation over P tilde of x, which is your distribution of your actual data set. And this is your encoder that produces these latent variables. And you have a prior that, and you want to make sure that the KL divergence doesn't exceed a certain threshold. So you know that the KL divergence between Gaussians is actually unbounded. So this is actually curtailing it in terms of how much it can actually blow up. So having a lower bound is not a great idea because then it's just going to go to infinity. But this is actually an upper bound. So what does it end up actually doing in practice? So this is just a 1D visualization of what it is. And here you've seen these kind of plots in the previous class where when the real and fake data are separated by a certain distance, it's very easy to learn almost a step function like discriminator and get no gradient for your fake data, which is what ends up happening here. So so let's say this is happening, and then there are ideas like adding noise to your instances, which we saw last class, where you can add noise to your input images and also to various features in your GAN, and make sure that there is some level of overlap between your real and fake data, especially if you add some kind of Gaussian noise. And then you can make sure that there is some kind of overlap, and so you're going to get gradients around these points, and then you're going to be able to play the GAN game better. So then you could imagine that the discriminator finds a less unit function like boundary, and therefore it's much easier for you to optimize. Oops. One second. I think it entered into the keypad. Okay. From okay. Sorry. So this is what is going to happen if you add instance noise, and so what happens in the variational information bottleneck scenario is something like you're bringing together the latent space information. Because you're having a latent space mutual information bottleneck, it's very likely that you're not going to capture all the details that let you easily figure out the real and fake data that easily. So that means that you're bringing the real and fake data, as far as the discriminator is concerned, much closer together. And so it ends up having an effect as if the real and fake data have some level of overlap in the latent space. And because we know from our studies on instance noise that having some kind of overlap is always good, because then the discriminator cannot end up being something like this. It has to be something like this. And so you get more gradients. And because you get more gradients for the fake data, you're able to optimize on the GAN game much better. So that's basically the motivation for using this kind of an information bottleneck in the latent space and making the discriminator operate with latents for the GAN optimization. And this is a very interesting idea, and it's been applied for the GAN optimization in a paper called Variational Information Bottleneck GAN, or VIB GAN, by Jason Peng et al. And Pieter will cover the results that this paper got on imitation learning. So more than actually producing pretty pictures, this idea was intended at trying to get imitation learning to be better. But the fact that GANs can be applied in imitation learning is a concept that we haven't covered yet. And so that's going to be covered by Pieter in the later part of the class. And so you'll see how the variational information bottleneck idea can make GAN imitation learning work even better. So this is not particularly meant to produce better images than a big GAN or a style GAN and so forth. It actually doesn't do that. So that's it for like normal GAN as far as like just producing unconditional class conditional GANs. Let's actually look at conditional GANs or pix to pix. So, but what do I mean by that is like you have a particular input image and you want to do some modification to it and produce a new version of that. And there are various versions of instantiating this. One is you have a black and white image and you want to make it into a color image. So that's what is shown in this slide. And you could, well, so there are various ways in which you could train these models. One is to just train a normal feed-forward model that just takes in your input image and produces your output image. And you optimize it with maximum mean squared error loss, which is treating every single pixel as a Gaussian independent of the other. Or you could use a softmax loss, or you could treat it as a conditional pixel CNN. There are so many versions of doing that. But the fact that GANs are really good at producing high resolution, high quality images makes them very attractive for this particular setting. So here's like a simple way to construct such an architecture, though I should say that in practice, a lot more details are involved, but we're just going to try to get across the high-level idea. And these slides are from Philip Isola at MIT, who's actually one of the pioneers of this technique. So this is what you would end up doing. You take a black and white image, you pass it to your generator, and you get some version that the generator produces. Now you want the discriminator to tell if this is a fake image or a real image. So if it ends up happening to be a valid color image, the discriminator would say it's real, or else it's a fake image. And you have a data set of real colored images. So the thing is, the generator is now trying to synthesize all these fake color images, and the discriminator is trying to identify the fakes. It's the same setting as a normal GAN, except that a generator is now going to take them as an additional input instead of just taking a z variable that you've seen so far. So you have an actual image, you have a latent variable z, and together the generator tries to use both of them to produce an output. So that's the only difference. And so the discriminator optimization, if you don't do any changes to the discriminator, if everything the discriminator takes is your generator produced output, all the real data, and it's just going to say if something is fake or real, this is going to be the usual GAN optimization for that. Now, there is a flaw with this particular approach. But before that, the high-level idea is you want to basically make the generator optimize some perceptual loss function, which the discriminator is learning. Because the discriminator is basically learning what is a real image or a fake image, and the generator is trying to use that discriminator as a loss function to optimize its output for. And that could be customized to whatever application you care about, which is a colorization application, or it's just like turning edges into an actual image and so forth. This is better, or it's like a learned loss function than, say, using a likelihood loss for your application. So, and this turns out to actually end up working much better than just using a likelihood function. So here is the particular flaw that I want to mention with just doing this. If you take a particular source image and you're using a generator and you end up with a target, the target could be any random colored image, right? So there are some bottles in this source image, but the target is some cat. And if you just feed in the cat to the discriminator, and if you feed in real images of various other classes to the discriminator, all it cares about is whether the generator produced a good colored image that makes sense or not. It doesn't care about whether it actually ended up doing the task the generator was meant to do, which is take the exact black and white image and just add color to it. So this particular objective, where the discriminator just cares about the output of the generator and does not care about the input of the generator, is a bad objective. Ideally, the generator should take in this and this together, and so the discriminator should take in the output of the generator and the input of the generator and figure out if the pair together makes sense, rather than just using the output of the generator alone. So, or else the discriminator could just keep saying, oh, this is a real image, and it could happily optimize. So if you just take the generator out for production, then it's just going to produce random images every time and has no connection with your input. So basically the idea is you now take the generator input as well as the generator output together and feed it to the discriminator and ask it to say, is it a real or fake pair, instead of just saying, is it a real or a fake image? And that's really why it becomes a new kind of model. It's called conditional GANs or pix-to-pix, because you're not doing image pair discriminators. So then this loss function no longer makes sense. You want to just you can't just use the output of the generator. So what you're going to do is you're going to take the input and the output of the generator together and feed that into the discriminator. So this becomes a convolutional neural net that takes in a pair of images and then says, does this pair make sense or not? That's the discriminator's job now. So now this makes sense, right? You take in your actual image, which is black and white. The generator managed to make a good colored version of that. And you want to say the pair together makes sense as a black and white and color image. And if it produces a cat, then you want to say the pair doesn't make sense, even if the cat was realistic, even if the cat was a good colored, realistic image. So that way, the generator is just doing its job rather than just managing to produce a data set of colored images. So this is basically the conditional GAN optimization. And the loss function now changes from what you've been seeing so far. The discriminator is going to take in a pair of inputs. But otherwise, the GAN architecture, the set of details required to optimize a GAN remain more or less the same. And this becomes the loss function. So one final term that's being added here is the L1 loss for a generator, which is something like an autoencoder, the generator being trained as an autoencoder, but with an L1 reconstruction loss instead of an L2 reconstruction loss. So basically, what is this doing? So this is making sure that if you have the generator and you're feeding in the input image and you have the generator, so you can also make sure that it trains as an autoencoder. And you want to make sure that the L1 reconstruction loss between these inputs and the outputs produced by the generator match. So why is this crucial? This is crucial because you want to make sure that your optimization is stable, sharp, produces sharp images, and L1 is usually a good idea to use for producing sharp images in your output. And this may seem like somewhat ad hoc and like a hack, and it's very hard to tweak what the lambda is. But it's been used in the conditional GAN setting for quite a long time in all of Alyosha Ifroz's papers, actually. So it could also be a legacy thing that people have been using for a long time. So one final aspect of conditional GANs is shrinking the capacity of the discriminator, making the discriminator as weak as possible. And so one way to do that is to make the discriminator focus on patches of your image rather than the full image. So that way it's less likely to pick up spurious patterns and cheat the generator. So people have tried to use things like multi-resolution discriminators, where the discriminator is looking at patches of various resolution from both the real data and the generator data. And so this is some technique that's been used to make this conditional GAN training pretty stable with good results. So here's another, so these are various works that have done that, and these are the results that you get if you use such a setting where you have you're trying to produce facades from some kind of cartoon-like image, and you have all these. If you use a 1:1 resolution, you get these very coarse, blurry image. But as you keep going to higher resolutions of patches, you get better and sharper images. So basically, the key motivation is to use fewer parameters because your patches are much smaller now. So that way you can share a lot of parameters across small patches, and your combinates don't need to be as big. And you have a lot more supervision and for the discriminator. And it's that way it doesn't, it's trying to optimize the way you want it to optimize. And you can also then scale it to like much larger images at test time. So there are like lots of good principles in using these kind of hacky patch-based models for the discriminator. So there are like a lot more tricks in conditional GAN setting, which is not possible to cover, just in one class, because it's not just a machine learning field anymore. Like there's a lot of people who worked on it from graphics, and there's like a lot of other tricks on how to prevent cheating, like how to use so for instance, the progressive GAN is one kind of a setting where it used all these ideas even in the regular image generation settings, and there's a lot of overlap across ideas in both these settings. So one thing we're going to look at now is see how there are like lots of cool applications. So always like generating cats is really cool. So what people did after Philip Isola and his colleagues published this paper was they made a demo where they took the trained model, hosted it on the web, and made people draw like edges of cat. Like since the model was trained to take an edge detector version of the image and convert it to the actual image, that means that artists could basically have these painting, like basic sketches, and those sketches will get some textures that are added by the GAN. And this is really cool because that way you can draw something. It's actually there on the web. You can go to the web and like go to Pix2Pix, edge to cats or something like that, and you can draw things and like it'll generate like cat textures of the same shapes. So this was made by Chris Hesse, and like so basically the way it works. This is not the actual demo, but I'm just saying that you just draw something and then there's like cat-like fur added on top of it. So people have used it to generate all sorts of cute and interesting things. Like you draw like a house or a cube, like all these weird shapes, and it generates as if it was wrapped up with a cat fur. It's kind of cute. And the other applications are just using it for colorization, which was also done by Richard Zhang and Alyosha Yufroz, people at Adobe, and then they have actually deployed it as a production technique. So it works really, really well. And there have also been applications on more like structured prediction, where the outputs are like an MRF, and it's more structured as a graph, and you really want to focus on the finer details, and it still works pretty well. Can't go into the details because there's a lot of other things going on other than the GAN models, but I just want to point out that these are other applications. And as a term, Pix2Pix is way more popular than just machine learning researchers. So this is actually a YouTube video of some artist who's using Pix2Pix, and it has like 4 million views. And then like there are like lots of videos like this, not just one video. So the term Pix2Pix is not even like a term that's only known to machine learning people. It's like pretty common. There are like millions of people in the world who know about it. Other than like like YouTube impact, maybe it's also been used for practical applications in medical imaging, where you can take MRI scans and use it to generate a CT scan of the same person, same head. So that's really cool. So that, because it must be really expensive to do it, and so if you already have done a previous scan, then it's very likely that you can get another scan done with just a GAN. So if you have a lot of data, you can train these kind of models, and it works pretty well. So that's it for like Pix2Pix. But all these ideas can be, it's just you can always figure out more and more ways to apply these and find cooler applications. So NVIDIA did that with this model called video to video, which is really cool. So let's watch it. So this is basically taking all this edge to image idea and putting it in the video setting. It's not doing it at frame by frame level, It's actually taking the video together and having a spatiotemporal model. The architectures are more involved, but the results are really cool. So you can basically see how you can get a high-level map of the city and cars, and then you can actually run a model. It's pretty close to reality, right? Like there are obviously ways in which you can find issues. So this is another scenario where you have the edge video and you have the input image, or the starting image, and then you can convert it to your actual video of the corresponding person. And you can, this way you can also do a lot of style transfer, extract the edges of one person, use the image of another person, and get the other person to see it, like act like they're saying the same thing with the same kind of facial expressions. And you can do it for, you can extract the poses of one person dancing, and you can take the initial image from another person, and you can basically paste those poses to the other person and create a fake video of the other person doing the same kind of dance moves.
In fact, Alyosha's students started a
Yeah.
company.
Yeah. I'm gonna show that video. Yeah. So these are other ways, other applications where if you have a semantic segmentation layout of a city and like a few frames of a car driving, you can actually then generate the rest of the video. And you don't even need to have these ground truth labels. You can use a pre-trained semantic segmentation, pre-trained supervised model, and use them to like run those models on top of an actual video and extract these high-level layouts, and then use those as a way to ground your video prediction model to be more consistent with your object level annotations. All right. So that's it for the video-to-video work. But again, yeah.
Yeah, so these, like, the person-to-person thing, it looks like it's susceptible to, like, like, for bad actors to use like deepfakes. So is there any research on, like, how we can protect it when it's
Yeah, so the question was that these kind of things can be misused for deepfakes and so on, creating deepfakes. And is there research to address those things? There is actually a Kaggle contest going on deepfake detection. I think that's being run by Facebook. So I think it's a hard problem, right? So generative models have advanced a lot. So creating deepfakes is not that hard, especially if you use all these middle annotated versions of the image, like poses and segmentation maps and so forth. So then the question comes to, like, the best way to address them is to perform a lot of it yourself and then train the classifier to detect whether this is real or fake. And it gets into this kind of adversarial setting, right? But then you could also say that, hey, if you can keep training better and better classifiers, I can try to figure out a way to cheat those classifiers by training those classifiers myself. And so it's a pretty hard problem to solve, and I don't know of any good solutions. And this is an even harder problem in like things like audio and text, because then it's much easier to produce like more consistent, realistic audio samples like WaveNet, as you've seen so previously. So people have used such kind of things to cheat like banks in terms of, you make a call and like get account details and so forth.
in general, is like the generator like more generalizable to different discriminators, or maybe is each discriminator more generalizable to like computers not out there?
I think that's like so more or less people have converged on standard practices for both, like the way you use conditional batch norm and projection discriminator and all that. But things like using multi-resolution discriminators, like for example, this video-to-video model, even though I didn't go into the details, it has a lot of these multi-resolution discriminators. And so those are not things that have been generalized to all possible generators. It's very application dependent.
Oh, I meant more like, so if I were to train like a GAN and you were training a GAN, would my discriminator work on your generator? Like would it
Oh, I see.
or would you like?
I think that's an interesting question. Actually, I'm not sure if that would work out. So obviously, a completely trained discriminator is not going to work out for a new generator. So it depends actually, yeah. So this is the thing that Pieter mentioned during the video, and I actually want to show this video too, which is pretty cool. This was done by Chen and other people at Berkeley actually, and this is pretty big enough, as close to 1 million views, and the PhD student who's an author on this actually started a company and rolled out an app that lets you do this, and I heard it's a pretty top-selling app on like iOS. So basically what this does is takes the source video, gets these 2D poses, and takes the target frame, tries to just recreate those poses and render those poses back in the target frame. And that way you can make a person perform dance moves of some source artists, which they wouldn't be able to do it on their own. So it's pretty cool. So the video, this particular one is not actually real on the right. Can we play the music? Okay. So you can clearly see it's jittering and all that, right, across time. It's still not there yet. So he's a PhD student who started this company that basically does this thing. Oh yeah, it's cool.
Lucky for you, that's what I like. That's what I like. Lucky for you, that's what I like. That's what I like.
So this looks pretty high frequency, and it's amazing that it's actually able to do it.
If you write anything
Oops.
on your
Yeah.
For these video results, like how fast is inference? Like, could you generate videos like this real time, or like how long does it take?
So the question is, how fast is the inference time? So I think when they published the paper, it was probably slow because they did it as a research project. But the PhD student who's part of that actually made it an app, so I'm guessing it's pretty fast now. So the other set of applications have been in the art domain, where it allows you to paint and convert it to really photorealistic images. So here is one application by NVIDIA called the GAN, which is apparently it's got a lot of traction recently. Has like 500,000 people who used it to create images. So basically the way it works is you can do these high-level semantic paints on the left, and it'll add texture and create it to an actual photograph that looks pretty realistic. So you can see that you can create some kind of grass and mountains and sky. And then as you draw these blue things on top, it creates a waterfall. Let's see. So there you go. It's adding mountains and rocks. Okay, sorry, rocks. And then you can add another rock. It's pretty semantic, so you can, all these colors are associated with actual objects. So you can see it's getting things like reflections, and it's pretty cool, even though that was not there in the high-level layout. And it can also be used to do things like rendering things in simulation, right? Game engines are using really high-resolution renderers, which have been written by actual graphics people. But now you could imagine that people who want to design new games could just create these high-level layouts, and the GAN would actually end up doing the rendering. And that could help people design new games, which are very photorealistic, much faster. And this is a really good business model for NVIDIA, I guess. So clearly one thing you would have figured out by now is that GAN is like not just a machine learning tool. It has a lot of, like you can create companies out of it. And so that's basically why GAN is so popular. It has huge traction, and every GAN paper is potentially going to be used in a product. There are negative consequences as well, like deep fakes, but there are also lots of positive things you can do, like the one you saw where you could create a CT scan out of an MRI scan. So we need to be thoughtful about it. Especially when you write a new GAN paper, you need to be pretty thoughtful about what are the potential use cases. So a final application that was that we want to show is this thing called learning to paint, or by DeepMind people, which is basically combining some form of reinforcement learning with generative adversarial nets, and using it to basically make an agent learn how to use a drawing software to create a data set, but within the rendering restrictions of the software. So you can see that. So this is actually, this video is going to play and you can see how it's painting the actual image using a particular rendering software. It's getting all these background things, and then it's adding all the detail over time. So this is actually an agent, and there's a policy that's doing this over time. So Pieter will teach you like how GANs can be applied in imitation learning. But those are the ideas that have been used in the setting where, so this was the original photo, the canvas, and it's trying to draw the same thing in the painting software. And it's obviously not going to match the realistic. It's not meant to be photorealistic. It's meant to be something like an artistic recreation of the same thing. And you can also see how it gets all these very minimalistic versions of your. All right. So that's it for applications. I mean, if you're inspired, you should just go and try a new thing and use GANs for it. So next thing I want to cover is how can we use GANs for learning good representations. And even though a lot of representation learning is uncovered yet, and we'll be doing it in the next couple of weeks, this is pretty good to learn and see what people have done in the GAN world. Especially remembering that DC GAN had all these cool vector arithmetic that you saw. So you can actually try to use GANs for learning good latent variable models. So the two models that we'll cover in this setting is InfoGAN, or information maximizing GANs, and BiGAN, or bidirectional GANs. Specifically for BiGAN, we'll just cover the big BiGAN version because that's what works really well, and the design is pretty much consistent with the original BiGAN. both of these papers were done, the InfoGAN and ByGAN were both papers done at Berkeley, and Big ByGAN was done at DeepMind by the same author who did ByGAN. So here's the high-level idea of InfoGAN. Now, this is an MNIST digit. This has been rendered. But then, what is it actually? It's just a bunch of actual pixel values in 8 bits across the entire resolution. But what you actually seek is some latent code that tells you what is the type of the digit, the class, how much is it rotated, is it to the left or the right, what is the width, basically you just want a set of factors that will allow you to recreate the digit with some kind of a rendering tool. And if you have ever written some kind of a renderer, usually you have things like shadow and lighting and all this pose of the object and so forth. So, and you run ray tracing to create your actual image. So those inputs to your rendering pipeline are basically what you seek as far as the representation learning is concerned. You want to go from your actual output to get the input to your graphics engine. And this version or this interpretation of representation learning is often referred to as inverting the renderer or inverse graphics. And usually people think of computer vision itself as the inverse graphics problem. So that was the motivation for InfoGAN. How do we create something like that with the generative adversarial net? So the way it works is as follows. You have a GAN, and it gets this noise vector Z. In addition to the noise vector, what if you also feed in some kind of a code? And that code should capture all these high-level aspects of your actual image. And your discriminator, in addition to saying real or fake, it's going to do something that's relevant to the code that you're feeding in. So before that, we need to do some math. Very little math, but it's pretty important. So what do we seek out of the code? We want the code to capture independent factors that let you explain maximally the variations that you see in your data set. Because only then they would capture things like, oh, this is this particular digit, and this is rotated this much, and so forth. So one way to do that is to use this mutual information tool. So think about the image X, and this is your latent code, and you want to have this mutual information term maximize. So you want to capture a latent code C that has as much mutual information shared with your actual image. And mutual information is just the difference between, both the directions are basically the same term. So you can write it as the entropy of your image minus the conditional entropy of your image on the code, or entropy of your code minus the posterior entropy of the code given the image. Where X is basically what the GAN generated, which is G of Z comma Z, Z comma C, because the generator is now conditioned on both the latent variable Z and this latent code C. So like always, mutual information is intractable. So you come up with this variational lower bound. And by now, you know how to use these variational lower bound math. It's just the same trickery always. You add and subtract a term, and you make sure one term is a KL divergence, and you always say that KL divergence is positive. And so you say this is a lower bound. So that's really what's happening here. So you're factoring this particular conditional entropy term as this dual expectation. And then you're adding this variational approximation to your probability distribution of code given your X. And what it ends up becoming is this particular term. This is some term that you can't really optimize because your code distribution is something you can already control. So this term ends up looking like a MLE for classifier regressor. It's just a maximum likelihood term for predicting the code given the image. You're having log Q C prime given X. So you're basically taking an image X, which is G of Z comma C, and trying to predict what is the code that actually would have produced this particular image. And you're averaging this over various X and over various C's that you can use for the X. So this is, even though you have this mutual information term and it's like, oh, there's a lot of math, it ends up working out very simply. And all it ends, as far as implementation goes, the only thing it adds is you have another loss that predicts the code given your generated image. And this is something that you can use the standard tools of neural nets to make sure that you have a single shared con net that you use for the discriminator. and it's both predicting whether the generated image is real or fake, generated in the real data, the real or fake task that you used with the normal GAN. So this is that particular term. And this is the additional term that you got with the variational lower bound for the mutual information, which you're trying to actually optimize. So that's really cheap to compute because, yeah.
But what's the code if it's data?
What's the code?
What's the code if it's data?
It's not the data. It's actually going to be something like a bunch of structured latent variables.
So like if your input to your shared content is data, you don't have a code that you're kind of matching to, right?
Oh, that's correct. Yeah. Then you're not going to have that. This is only for the generated data. For the real data, you're just going to use the regular GAN objective, which is the discriminator saying it's a real. Yeah, this is only, so because this particular term is just for your generated distribution. Yeah, that's correct. So note that you're trying to maximize this, and therefore you're trying to minimize this. So what does that actually mean? You're trying to minimize the conditional entropy of the latent code given the generated image. So basically what it means is once you see an image that's been generated by the GAN, you should be able to say what is the latent code that should have generated it. There should be very minimal uncertainty about it. That's what it means is maximize the mutual information between the latent code and your generated image. So for instance, if you see an MNIST digit and you know it's 1, so then you already know that the latent code is 1, for the digit class is going to be 1. There's no uncertainty anymore. And if it's been rotated like this, then you know that that's the rotation angle. So if you reduce this entropy as much as possible, then it means that you can recover the latent code from your actual image with minimal uncertainty. So maximizing the mutual information ends up amounting to minimizing the conditional entropy of the latent code given the generated image. So the more you try to do this objective well, and the less latent codes that you can use, what ends up happening is each latent code ends up capturing very different aspects of your data, which is a property referred to in machine learning as disentanglement, which is that you have a lot of latent variables, but you want them to capture very different things about your data set. And it's very intuitive and elegant that way because you have a lot, you don't want your factors of variation to be very entangled, and because then it's not clear which one is capturing which aspect of your data set. And InfoGAN has these really, really amazing qualitative visualizations for disentanglement. So this was a 3D data set, and basically the y-axis is varying the Gaussian, and the x-axis is varying a latent variable C1 that's been structured to lie within a certain range. And you can clearly see that as you keep varying C1, the same object is preserved, but it's just having all these different geometric layouts, like your pose is changing. And it's uniformly changing across all these different Z's. So it's changing the Z's is going to give you a different object. But just retaining the C and changing the C is just going to retain the same object, but change its geometric aspects like the pose. And similarly, you can also change the size. So this is a really big object, and it's the same chair, but it's getting smaller and smaller as you change the other variable. And as you change Z's, you're getting like a different set of objects, different chairs. And you can also use it for phases, and it generates, you can vary the emotion. This looks like a pretty sad or angry or like, poker face, and then you go all the way to a smiling face. And these are generating different phases, different complexion colors, and so forth. So you can also see things like absence or presence of glasses. So one could ask, like, hey, you've seen all this in DC GAN, so what's new about this? The new thing is that these are all being captured by independent latent variables. So these are all different latent factors. So this is a separate latent variable, this is a separate latent variable. So the fact that independent latent variables can capture these different aspects that are contained in your data set is very elegant. And that's the most nice property of InfoGAN, which is that you can do disentangled representation learning very efficiently within the GAN framework. So how do these things actually scale? Like if you feed in a categorical variable that's roughly representative of the number of classes in your data set, could you actually get something that produces a different class image for that particular category at the scale of ImageNet? So Jeff Donahue did this experiment with the big GAN, and it turns out to be true. So in a big GAN, instead of just feeding in a Gaussian variable, which is the usual GAN setting, if you also feed in a uniform distribution categorical variable of roughly the number of classes of ImageNet, which is 1024, the number of classes is actually 1000. So this amounts to 10 bits of information. So then even if you don't have all this mutual information objective at all, if you just do the regular GAN training, it ends up being the case that you could optimize, every time you feed in a different value of this categorical variable, you end up with a different class. So along the x-axis, you're actually varying the z, and along the y-axis, you're varying the categorical variable. And you can see that different rows are producing different classes, and along the columns, you can see various variations of the same class. And this is completely unsupervised. So GANs have this nice property that you feed in some additional conditioning information, it's roughly trying to plug in that relationship automatically while it's optimizing. So you can see that it works very high resolutions and like very large number of classes. Caveat, obviously, to even know that this is possible, you need a lot of compute. But then it's great that all these methods are scaling really well. So what is the idea of a bidirectional GAN? The basic premise is as follows. In a GAN, you just have a graphical model that takes in your latent variable and converts it to your actual image. So, but for a representation learning perspective, you want to go from an image to its latent. And you actually want an encoder that takes in your pixels and you convert it into some kind of a vector that you can use for a downstream task. So what the idea in bidirectional GAN is basically to do exactly that. Just like how you have a generator that takes in a z and goes to x, you also have an encoder that takes an x and puts it into some latent variable distribution z hat. So you saw that in pix2pix, and you saw like in other places where if you feed in more information to the discriminator and ask it to use more information, it ends up doing good things. So that's what happens in the discriminator, where you're feeding in both the x, which is like here, it could be real, this is generated, and then you could feed in your actual latent, which you sample, you use to sample, and then here you could feed in your encoded latent that you have from your new encoder. And you feed in these pairs of information to your discriminator, and now the discriminator is asked to score a real or fake for this pair. So that ends up doing something very similar to this conditional GAN setting that you saw, except that instead of feeding two different images, you're feeding in an X and its corresponding latent. So this way, your discriminator is now aware that this generated image is using this particular latent, or this real image has been encoded into this particular latent. So because it's aware of this, it's trying to learn a good representation in addition to learning a good generator. And that is basically the idea of bidirectional GAN. It's doing two directions. One is going from Z to X, and the other is going from X to Z. So that way, you can use the final G that you get as a generator and sample images from it. And you can use the final E that you get as a representation learner and use it to fine-tune for other downstream tasks. It's a very elegant model. Any questions on this?
For all these GAN models that use a smaller latent space than
Yeah.
input space, do we have to do some sort of information bottlenecking on the discriminator? Because otherwise it would just like get the high-level details and be able to discern pretty easily whether or not something's real or fake.
So the discriminator is using a ComNet to take your image and do the classifier or scoring task. The bottleneck idea is to take just the latent, but it's not a conventional design principle used in GANs. There are various other ways to weaken or cripple the discriminator or like condition it well. Like in the previous class, we saw ideas like Lipschitzness and spectral normalization. And then there are ideas in the pix2pix literature of using patches. And so this is also good, like feeding in an additional latent. So you're not like cutting the path to the X, you're still feeding in X. So every time you would feed in X real and encoder of X real, which is your new Z, or you feed in X fake and your Z that you actually use to generate the X fake. And so the discriminator is going to look at both the pairs and do the task of scoring whether it's a real or a fake pair. It's useful. So I show you that it actually helps in unconditional image generation. So big BiGAN. So if you do this, if you optimize it with a large batch size, a lot of TPUs, big images, you end up getting like really, really good samples. These are unconditional. Previously, you saw big GAN samples, which are conditional on the class. I think it's pretty much the same sample quality, but without any labels. So that means that the encoder is learning really, really good representations. And it also works at high resolution, so 256 by 256. So the basic way it works, as you saw, is you take the latent sample, use a big generator. Big GAN generator is like a giant COMNet, and then you get the generated image. And then you use the encoder, you take in the real image sample, put it into a predicted latent, and then you take this particular discriminator architecture that takes in these pairs of information, produces these unary score terms for X and Z separately, and then tries to combine them with the paired information and produces a loss. You should check out the paper for how the architecture is actually built, because a lot of experiments and thought were put into it. But let's just say that if you do everything right and you do this carefully, you optimize it well, it ends up working pretty well. So, and the reason it's called a bidirectional GAN is because of this two-way connections between the X and the Z. So how does it work as a representation learning pipeline? We've not covered what representation learning is yet, but I still want to highlight that a very simple test in representation learning is whatever encoder you got from your unsupervised objective, you just put a stop gradient on it. You just freeze those weights, take a linear classifier, put it on top of those features, and see how much the linear classifier can get on an actual classification task. So this basically is a test of how semantic your features are, because a linear classifier is really weak. So if your features are really good, then even a weak classifier can work well on top of those features. And it turns out that big BiGAN, even though it's just a very generative objective, it can produce a really good top one score of 61.3 on ImageNet. This is really far away from the kind of supervised accuracies you see on ImageNet, which is like 76%. So it's not that great, but it's still amazing that with just a GAN that's been trained with this additional encoder, that encoder ends up capturing really high-level semantics that you never expected to capture with your objective. So here are some qualitative visualizations. So you can take the latent space, you can take a particular image, and you can just do nearest neighbors in the latent space. And it ends up drawing very similar images. So this is the anchor image on the left. And then these are all the nearest neighbors that were sampled from your data set. So basically, you would just do nearest neighbor in the latent space, and then you would forward prop your generator with those nearest neighbor latents, and then you would get these new other images. So you can see that how it's able to retain the class information, and is able to make sure that all these nearest neighbors are pretty much semantic and like in the same class. So the other cool thing about this, what I like the most about big BiGAN, was the fact that you could do semantic reconstructions. So in BiGAN, you're not learning any reconstruction or an autoencoder. You're just learning an encoder that takes X, puts it into some latent variable Z. But you're also learning a generator that takes in some Z from a Gaussian and creates an image out of it. So one thing you could do is you could take an image, you could map it to a latent, and then you could feed in that latent to the generator that you learned and see what you get as a generated image. So this is not exactly like an autoencoder reconstruction, because there is no connection between the encoder and the generator you learned except for the discriminator optimizing them together. So you're obviously going to see something different, but it's very nice that the semantics are preserved. So this is one particular ape, and it's producing another very, very different kind of ape. And then, so you can see how the same class is preserved, and like I think this is pretty much the same dog breed, but it's producing a different dog. And It's retaining the class that there is a person in a very there's a lot of snow around, but then it's producing a different person, a different scene. So that way you can see that. Yeah, you had a question.
Is there any obvious relationship between the like when you take your encoding and you do your representation learning loss on images? Is there any clear relationship between the places where it has error there and like where it has low support, like as a generator?
I didn't quite get it.
Like GANs generally have low support compared to the data distribution.
For the discriminator, as far as the discriminator is concerned. Do you mean the discriminator score?
I'm talking more about like the representation that it learns. Is it only particularly good for the areas where it has like support?
Oh, I see. So are you saying would the representational learning work if you fed in a generated image instead of a real image at test time? Is that what you're saying?
I'm mainly asking like, is it going to fail if you feed it in some image that's not in the support region?
Oh, I see. Is it robust to like auto distribution? Probably not. I think it's just going to learn. I mean, you know that GANs still overfit, right? Like there is a lot of mode collapse, so it's highly likely that they're not great for if you just throw in a random image. But then fix to that is to just train on more data, right? So then you could make the GAN better. So these are reconstructions that, like the way I said, you take in an image, you get the latent, and then you feed the latent to the generator. You get the latent from the encoder. And it's able to produce the same class, but different images of the same class. And I find it really, really nice. Like the fact that this even works is really amazing. And that really means that the Z is captured the class, and it's retaining the class information. It's just not linearly separable, so the linear classifier scores are not that great. But in terms of a representation learner, it's really good. And it's really working well. Okay. So that's it for my part today. But then I'm guessing you have questions, so I can take some questions on, because Pieter is going to cover energy-based models of GANs, and it'll be a pretty different set of slides from now. Yeah.
For those dance transfer videos, how do you ensure temporal consistency? Does the discriminator take a stack of frames?
So that's a great question. So how do you ensure temporal consistency for all the video-to-video stuff? So that's why so the discriminator does take a stack of frames. Like the architecture is a little more involved, and we didn't go into the details. But again, I don't think even that is just enough. The fact that they use all these high-level information like semantic segmentation layouts in the NVIDIA case, or edges, post detectors, and in Alyosha's work as well, using the actual human pose, they actually have these post-matching losses. So you take the target image of the person that you want to produce the video for, you extract the pose of the target person, you have the poses of the source person, then you do some kind of complicated source retargeting to align those source poses to the target poses. And then you predict the future target poses that you want, and you then use those poses to render the actual future. So it's a pretty involved model as far as the details goes. And just taking a stack of frames and trying to output another stack of frames is very likely not to work. And that's why people end up using all these extra information. In the NVIDIA case, they use semantic segmentation inputs. And the discriminator, as well as the generator, is conditioned to use that information in addition to the actual image. And it's also using multi-resolution inputs. So that way, it's like pretty structured and low-level details. Yeah. Yeah.
Question from the 5-big GAN thing.
Yeah.
I didn't quite understand. So you have your encoder and your generator, and they're kind of doing opposite things, but like the only reason that they're sort of inverses is because the discriminator is like optimizing them, right? Is there any reason not to just try to like encode an image and then generate it back or something, and try to make that signal consistent?
Oh, you mean to say you encode the image, get a Z, feed that exact Z to your generator, get the output, and then make sure that the output matches the input. That's just an autoencoder, right? Or you want to do it with the GAN objective instead of mean squared error. So there are versions like that, like things like adversarial autoencoders, and I think adversarial autoencoder is different, but there are things that try to do something similar to this, where there is an autoencoder like model, but it's being optimized with the GAN objective instead of the mean squared error. Those things work too. It's just that I think nobody has pushed those models to the quality that has been shown in big BiGAN. And there's more math in big BiGAN that's probably like something we can't cover in class, but you should definitely go check out the original BiGAN paper. And so yeah, there's no actual reason to prefer this over the other. It's just that this really works well. Yeah. Any general questions on like GANs so far? Like as a practitioner, like if you're interested in using GANs for something, what do you care about, etc. Yeah.
In general, how hard is it to like get these models working for something different from like whatever they're choosing for?
So yeah, how easy is it to take a GAN and make it work on a new domain? Not as hard as it was 2-3 years ago, of course, but certainly you need to delve into the details, right? Like for instance, if you're doing something like pix-to-pix, it's much advisable to use the architectures that have been adopted in the pix-to-pix literature. So I didn't go into the details, but in pix-to-pix, people use something like a UNet to generate the generator takes the source image and produces the target image. But it's not just like you take the source image, put a bottleneck, get it into some latent space, and then generate the target. It's much more structured and uses something like a UNet with skip connections. And that actually works the best. If you look at the CycleGAN code, they actually use a UNet. So these are things that have been coming out of like other things in computer vision, like image segmentation and semantic segmentation and all that. So it depends a lot. So if you're doing pix-to-pix, you would go and look at the open source code and try to adopt the same set of architectures. But if you're doing something like BiGAN, if you're trying to do some unconditional things, you would rather use the same kind of architectures they used. So if you follow all the details and if you just use pretty much the same things, it's very likely that you get it working for your domain too. But again, like for instance, like the question Ajay asked, like if you're trying to do some video-to-video kind of things, then it's like much more involved. Like how do you do all these post extractions? Then you need to have pre-trained supervised models for that. And then that gets pretty low-level details, right? Any other questions? All right. That's it for GANs. Pieter will do the more exciting part of GANs.
I don't know about that. So we've covered GANs, and we've covered a lot of the kind of practical things, at least at a medium-high level, that you need to get GANs to work. What we haven't looked at much is some of the theory behind GANs, as well as some other applications of GANs and adversarial losses. So let's take a look at that now. I think the cleanest theory behind GANs is actually through energy models. And we haven't covered energy models. If you had been doing deep learning around 2004 to 2011, could be 2 PhD spans, really, you would have probably worked with energy-based models. They were very popular, Boltzmann machines, wake-sleep algorithms, all those things. And then they kind of disappeared. But it turns out that GANs can be seen as an energy-based model. So let's do a quick recap of what an energy model is and then see how it can phrase GANs that way. So in an energy model, you associate a probability with a, let's say, an image x as e to the negative energy of x. So this is a bit how people think in thermodynamics of ground states of the world. In thermodynamics, you could have many possible ground states of the world x. Each ground state has an energy associated with it. the lower the energy, the higher the probability. The higher the energy, the lower the probability. So very high energy, e to the negative high number will be close to 0. And then, of course, because it needs to be a distribution, you need to normalize by normalizing constant z, which looks at all possible world states or all possible images, and then says, okay, what's the joint e to the negative energy of all of them summed together, and normalized by that. So the practical challenge with energy-based models is that when domains are very large, computing z can be tricky, and domains get large very, very quickly. So let's take a look. 28 by 28 by 3, so RGB 28 by 28 image. That's tiny. I mean, that's not a high-resolution image you're trying to generate. So one channel, 8 bits, so 256 possible values a single channel entry can take on. Then to the power 28 times 28 times 3 is this number over here. You look at it, you're probably not used to looking at 256 to the power 2352. So I tried to put it in the calculator and see how much that is. Calculator said infinity. So even for a really tiny image, 28 by 28 by 3 channels, the number of possible images apparently is infinity up to rounding error. If you look at the actual number, it's roughly 10 to the power 16,464. The number of atoms in the universe is roughly 10 to the 80. So this is a large number in many ways. But in terms of image size, it's tiny. What it means, though, if we go back to energy-based models, the z here is just impractical to compute, at least exactly, because you cannot sum over that many possible images, compute their e to the negative energy, and then get your z out. It's just going to take way too long. So we'll have to figure out the way to approximate that z. A little more about that very soon, but let's make this a little bit more concrete. What does an energy-based model look like in the context of neural nets? It could be something where you take in an image x, process it by a bunch of layers, and then output the energy of that image x. And you parameterize it by theta because the weights in the neural network can change, and depending on your choice of the weights, you will get a different energy associated with different images. And so likely what you want is low energy for real-looking images and high energy for things that don't look real, and then your probabilistic model will put high probability on the things you want and low probability on unrealistic things. So now that we have this formalization, we can actually do maximum likelihood estimation. Well, at least we can phrase it that way. We can say, let's maximize expectation under the data distribution log probability under the model p theta of x. Okay, we maximize that. What is under the hood? Probability of x is e to the negative energy of x divided by the normalizing constant. Often people write just z. I wrote explicitly z theta because z is the sum over all possible x's e to the negative energy parameterized by theta of x. And so z does depend on theta. And then if we take the log of a ratio, it's the, well, subtraction of the two things in the ratio. So we have expected value under the data distribution of the negative energy. We're maximizing that, so we're sometimes trying to minimize the energy of all the data points, which makes sense intuitively. And then we have this counterbalance here in that we need to normalize still. Now, z is hard to compute. In fact, impractical to compute exactly. So how about we just ignore z and maximize the first part of the objective? Any thoughts? So if we ignore z, we can make the output, we want low energy, so we can make the output really low for everything. And then if we ignore z, that's great. But then actually we don't learn to distinguish between likely data and unlikely data because everything is just given a low energy score because we're not normalizing. Actually, can somebody close the door? Thank you. So we can't ignore z. We need to incorporate z or at least some approximate effect of z, otherwise it's not going to work. Bless you. Now, let's take another look at z. Actually, let's see. you should kind of see what's coming in some ways. What is Z? It's a sum over a lot of terms. A sum is like an expectation. An expectation we like to approximate with a Monte Carlo sample estimate. But right now, Z is a sum over, if we go back to definition of Z, it's a sum over uniformly all possible x's. Well, if we're going to sample uniformly from all possible x's, it's not going to be very interesting. We're going to want to sample somehow based on things that are important. So we're going to do something like importance sampling, bring in a variational distribution that makes our samples come from the right thing, and then we can approximate Z. So let's do the math. We have log of Z that we're trying to compute. Then this is just a definition over here. Next step, we multiply and divide by the same distribution, q phi of x. And this ultimately is going to be some kind of neural net that we control with parameters phi. Well, we now have an expectation here with respect to this distribution. So let's write it that way. Then we do the Jensen's inequality thing, the log of expected value of x is bigger than or equal to expected value log of x. That's this thing over here comparing this with this. So the log of the expected value is higher than the expected value of the log. We also know that if we choose the optimal q phi, meaning the exact optimal, so maybe a parameterized distribution q phi cannot achieve it, but the exact optimal, that this will hold with equality. It holds for all q phi's, the inequality, but since it holds for all, it holds also for the one that achieves it as close as possible, the max one, so that's the one we want to find. We're not going to find the actual max because we're going to parameterize our distribution q, but within the parameterized family, we're going to try to find the one that maximizes it. And so we have this quantity over here where the log of an exponentiated quantity is just the thing that was exponentiated. That's the first part. And then the, oh, what happened here? This should have been a expectation, x according to q phi. So, and then we have the, here also an expectation of x according to q phi. And then here we have the entropy, which is expected value q phi under q phi of negative log q phi of x. And we have now this bound on our negative log z by flipping the sign on both sides and flipping the bigger than into a smaller than. Now that we have this, we can sub this back into what we had before. And just for a moment here, what do? We'd start from an expectation under a uniform distribution over all possible x's, which if we sample from it is not going to give us a very representative estimate because we will probably sample the wrong x's, to if we choose the right variational distribution q phi, probably from a relatively small number of samples, we'll be able to get a decent estimate of the partition function. So when we then go back to our maximum likelihood objective, we can now look at the minus log z part and fill in what we had. And if you look at it, this is actually the GAN objective. So let's take this to the next page. What do we have? We have the, if we just look at the first part, we have maximize over theta, minimize over q phi of expected value under the data distribution of negative energy of x coming from the data, and then contrasting that with the energy of x coming from the generator distribution q phi. So remember the W GAN objective? It was, we called it D, and we called this guy over here D. But other than that, this essentially looks the same, right? It's just that now we call it E because we derived it from an energy perspective. But ultimately, we're just looking at outputs of a discriminator and try to make it as different as possible between data and generator distribution. Then we have this extra thing over here, and we see that the generator actually has to do something extra. To properly optimize this energy-based model likelihood, we also have to look, we minimize over Q phi, so we minimize the negative entropy, which means we maximize the entropy, and so we have to maximize the entropy of the generator distribution. It's kind of interesting that this comes out. A lot of people put it in in a hacky way already, because they say like, oh, whoa, mode collapse, need more variation and more variability. Let's add some weighted entropy. But actually, if you just do things cleanly and right, it's already there. You don't need to, after the fact, add it in if you derive it, what I think is the cleanest way to derive GANs. Now, it's all nice to have the entropy there as the extra term. Is it easy to compute? Generally, no. So it's beautiful, but in practice, that term will often not be tractable. So even though we now know that to do it right, we need to put it there, it doesn't mean we're able to do it. There are exceptions, of course, and it's really worth investigating. So you could think about, where can we compute the entropy? Any thoughts? So softmax, we can compute the entropy, right? So if a discrete output, softmax. Now, softmax, in the naive way, would just be a histogram distribution, which is not that great to have, but something very close is pixel CNN, right? Pixel CNN has a softmax as every step along the way you generate a pixel. And so actually, if you had a pixel CNN, you could exactly compute the entropy. It's just the sum of the entropies of every step along the way. You could exactly optimize this objective. And so you could actually do an energy-based model where you have a discriminator that is just like every other GAN discriminator, and your generator would be a pixel CNN generator. And you could do it exactly the right way as an energy-based model. There's a little bit of a pitfall that makes it maybe hard to do in practice. Any thoughts what that is? Alex? So one thing is, if you want to evaluate these expectations, you might have to go over an exponential number of them. Infinity, according to the calculator, right? That is true, but as you're sampling from a variational distribution here that's optimized pretty well, it's okay to use a Monte Carlo approximation. So that part will probably be fine. So maybe to highlight this a little bit more, this is an expectation. So we can evaluate an expectation. The entropy over here indeed has a summation over all possible values, but that's also an expectation of x according to Q phi of negative log Q phi of x. And so you could approximate the entropy with a Monte Carlo estimate. The question is, can you efficiently calculate log Q phi of x? And if you can, then you can start doing this. And so in a pixel CNN, you can, because you have an exact likelihood. And so you can compute the entropy exactly. If you have a flow model of the right structure, you can do this too. And so there is ways of getting the entropy out, at least a Monte Carlo estimate of the entropy. The thing that's slightly tricky, if you use a pixel CNN model, and I do encourage you to try it if you have some time to spare, but the tricky thing is that pixel CNN was really nice because you could, in one forward pass, have a loss on every pixel. But sampling was slow. To evaluate this is GAN training. You're going to have to generate a bunch of samples. And after you generated some samples, you're going to do an update, right? Both for discriminator and generator. And generating those samples will take a real long time because to use this loss, your pixel CNN will have to generate samples every time before you get your mini batch together, and that's going to take many, many passes through the network. So you'll have to think carefully about how to do that efficiently, save time somewhere, somehow. But other than that, pixel CNN allows you to do this. And probably flow models allow you to do it too. I haven't seen it done exactly with an entropy in the objective, but it's likely it's possible. So if you're curious about digging into this a little deeper, the first place I would recommend you look is actually this write-up over here. This is an unpublished write-up that I asked that John Schulman made 4 years ago. And I remember it from 4 years ago when he showed it to me, so I asked him a week ago if any chance he could put it online, because I think it's an example of a write-up that's just really fun, clear, and that makes you feel like, yeah, this really explains it completely the right way. It also has ideas about how to measure progress on when you optimize min-max objectives like GANs. It actually introduces a regularizer on the discriminator, so you actually get the whole pretty much whatever the spectral GAN or WGAN Lifshitz stuff is pretty much already in there, even though it happened long before it was invented. It's an example of an unpublished write-up that foreshadowed a lot of things people would invent later, independently, obviously, because this was not published, but giving it out in an extremely clean way. So highly recommend checking this out. Yeah, download it before John might remove it from his website, intentionally or by mistake. Then in terms of work that's been published around that time, both out of Benjo's group and Jan LeCun's group, there were papers drawing the connection between energy-based models and GANs. The connections were not as closely and as tightly done as in John's write-up, but there were very clear connections made and very nice images generated with the algorithms they proposed. Then more recently, there are some related papers. There is one here where it's looking at, essentially, let's add an entropy term to the GAN objective, which we know from energy-based modeling and doing the full clean derivation is actually there to start out with. But here's kind of just added as a regularization term to try to avoid mode collapse. But the main contribution of the paper is not so much adding the entropy term, that's understood, that should help, but it looks at variational autoencoders and shows an approximate way of computing the entropy term for a VAE, and also an approximate way to get gradient estimates on that entropy term so you can actually optimize the objective when you have a VAE as your generator. And then this one here does something with combining flows and GANs. They don't really have the entropy term in there as far as I can tell, so it's not the full energy-based derivation, but it does look at how you can have a flow model for your generator and a discriminator and put it all together in a GAN objective. But yeah, I would say, if you have any time to spare, definitely go read John's write-up. I had a lot of fun rereading it, and I think it's the kind of thing when you read it, you feel like, okay, it's very inspiring to maybe write a write-up like that in the future sometime. That's still, 4 years later, still valid. Any questions about the energy models in GANs? By the way, you're supposed to come up with final projects, so one possible final project would be to think through how you can do entropy calculation and gradients for flow models or for pixel CNNs in a way that's maybe reasonably tractable, and then see if it can compare the generation you get with a generator trained that way versus generator directly trained with maximum likelihood. Because in principle, once you have a pixel CNN generator, you can just train it with maximum likelihood directly, or you can train it with this discriminator energy-based model objective, which is different training losses. And so it'd be interesting to see how do the pictures compare to each other. Is it possible that maybe the discriminator helps guide the training of the maximum likelihood model, that it's a good regularizer? These are questions that we don't have answers to and that could make for a good final project. For the flow models, the interesting thing would be to investigate how do you tractably get the entropy out? What structures of flow models allow you to get good entropy estimates and gradients of those entropy estimates? Okay, so there's another idea that we haven't, oh, question, yes.
You don't mind.
Go for it.
So for these entropy regularized models, when they recapture modes, do you have any idea if not only do they recapture modes, but would they sample randomly with approximately the same densities at those modes?
Well, I mean, it all depends on the quality of your generator and discriminator networks, right? In the extreme case, if you fully optimize this objective, at the solution, you put, let's say there's a finite set of images or some manifold of images that are reasonable. There will be a relatively low and maybe uniform energy on each of the plausible images, and it will be a infinitely high energy on anything that's not a plausible image in some way. That's the extreme case you end up with. Will you fit that? Probably not. You'll have finite data. You don't want to, on your data, have uniform on the data, infinite energy on everything else, because then you're overfitting. So in practice, it depends a lot on the details of your architecture, how expressive, how you train it. But in principle, when you optimize this objective, it should cover every mode. If it doesn't cover a certain mode, it will have a lower score than something that does cover all the modes, because covering all the modes will be higher entropy, and that will increase your score. Also, will make it harder for the discriminator when you cover all the modes. Okay, so another thing we haven't really touched upon is the connection between GANs and optimal transport. We kind of have, actually. What we did is the Wasserstein distance, or the Wasserstein GAN. We had this Earth mover distance thing, and what we looked at was this quantity over here. Now remember what that means. Essentially saying we have two distributions, P real and P generator. And for these two distributions, they'll both generate samples. And we're curious to measure how different are these sets of samples. And what we're saying here is that what we can look at is if I have a sample from one distribution and the other, I can measure distance, x minus y, with some distance metric. But the infimum here says that effectively I can take any permutation, saying I generate infinitely many from one, infinitely many from the other, then I can find the perfect permutation from one side to the other side, and after I've found the perfect permutation mapping from one to the other, what is the distance left? So I try to match everybody to their closest neighbor in some sense, and then I see how much distance is left. And if they're the same distribution, there will be no distance left. If they're different distributions, there will be some non-zero distance left. That's what this thing is measuring. Then we said, oh, we should go to the dual and do what essentially became just a standard GAN, oh, I forgot to say one thing. Talk about standard GAN. So this thing over here, you look at it and you say, oh, this looks like a W GAN objective with one energy minus the other energy. It turns out if you look at John's write-up, he will show you that if for your energy, you actually take the log of the sigmoid of the discriminator, then you get the regular GAN back out. And so just taking the right loss function on your discriminator or energy model, how you architect the very last part, will turn it into any of the variations pretty much of GAN models that we've already seen. So this energy-based derivation does not just lead to the W GAN objective style GAN, it leads to all the others too. It's just a matter of how you architect the very last part of your network, and that'll result in whichever version you want pretty much. So in our case, when we looked at this Earth mover distance, said, oh, the dual is something that gives us a more GAN-like objective. Let's use that. Don't have to do that. You can actually do something else. So what you can do, and there's a couple papers that look at this, you can actually just generate your samples. You can look at the data. You can try to find an optimal permutation between the two. And then once you have done the matches, you can try to bring them closer together. And so you train your generator to bring them closer together. You train your discriminator to keep them apart. So there's a couple of papers that look at this, and we'll look at a few examples, very specific ones. We'll look at implicit likelihood and moment matching, which are two specific instances, but essentially the same idea. Generate a bunch of stuff, you have your data, and you find the match between them. So here's implicit likelihood models. You draw samples from your generator distribution. Then you pick some subset of your, so this is the data. This is your generator. And then you just find an assignment. You look for every real data point. So for all the real data, for all I in data, you find the closest match among the ones that were generated. After you've found the closest match, you do an optimization. You will look at that closest match. You will look how that depends on the generator parameters and you will then optimize the image that you're generating and move it closer to that closest data point that was matched to it. It's possible you match 2 data points to the same generated image, in which case that generated image gets pulled into 2 directions at the same time. It could be that you just match 1 data point to a generated image, and then that generated image will just move directly towards that data point. What does this do? What it does is that one of the big things people worry about, again, GANs, is mode collapse, and this thing is ensuring it can't really happen because every data point will have some pull and pull at least one of your generated images towards itself, ensuring that all your modes are at least trying to be covered. Of course, you might need a lot of gradient steps before you get there, but it ensures that no data point is left behind. You're pulling towards every one of them. And then you repeat. So that's one way to do it. You might say, well, how are you measuring this distance here? Is this pixel space? What's going on? There's a bunch of variations that look at this. So moment matching is one way to measure that distance in some kind of specific way. So in moment matching, you again have data that is sample data, then you generate data. You're going to have to find matches. After you found the matches, you need to somehow measure distance. So one way to measure distance is to just say, hey, I'm going to look at the average of both of them. So you're not even individually matching them. You're just saying, let me just look at the moment of the distribution, the first moment. But you could do the same thing for the second order moment, third order, and so forth. Now, higher order moments are going to be expensive to compute, so it might not be practical. But if you go to essentially infinitely order moment, you are matching the distributions completely. In practice, people will do first, maybe second order moment matching. And so that's a very kind of simplified way. You skip the permutation finding. You just say the means should line up in feature space, and that's what we're optimizing for. The kernel trick is this thing where essentially, well, if you look at this here, it's in feature space. And if you work out this norm, you get inner products between feature vectors. If you have inner products between feature vectors, you can do something called kernel trick, which says, oh, I can just compute a direct similarity measure, k, between 2 inputs, xi and xj. And if that similarity metric satisfies certain properties, then I'm good to go, and I don't need to first generate feature vectors to then do inner products. And often that can be more efficient than going through that feature space. For example, if you want to measure similarity this way, the actual feature space is infinite dimensional, but this thing can be computed much more easily than going to infinite dimensional space and then inner producting to get out the number. So people looked at this. There's a paper from Richard Zemmel's group where they try to compare this way of training with regular GANs. It generates some reasonably realistic images. It's not one of the, I would say, winning directions at the moment, but there's interesting ideas in there, so I want to highlight it because maybe in the future there are ideas I can build on top of this that could help current systems work better. So the kernel, of course, is a bit of a choice you have to make, and in some ways it kind of sidesteps the notion of learning a discriminator. You now somehow pick a kernel, but it plays the same role. Maybe it's easier to pick by hand. Maybe you still want to learn that kernel. Then you're kind of back to a two-player game. That's up to you. OK, so those were a few variations really on GANs looking at matching distributions from samples. Then just 2 more things I'd like to cover on GANs. One is that there are other uses of the adversarial loss. One use is transfer learning. Imagine you have labeled images and you have unlabeled images. And imagine that this part is all identical. Whether it's labeled or unlabeled, you process through the same network. Then here you have some kind of loss that says, I want in the feature space over here it to be indistinguishable whether I came from my unlabeled data set or my labeled data set. For example, my labeled images might be from simulation. In simulation, I can generate a lot of labeled images very easily. These might be real world, and so I don't have a lot of labels or I have no labels at all. And so what I'm then doing by this adversarial loss over here, I don't want to be able to distinguish between a hidden feature layer from one or the other. means that you have to erase anything that is indicative of the source, sim or real. Once you erase that, everything that comes after here will build only on things that are shared. And so whatever you learn over here will also be applicable on this path over here. And so this is a way to, in some way, align data from different domains. It could be sim and real, it could be indoor images, outdoor images, it could be different data sources where there's just other statistical properties that are different between how you collected the data, and then at some layer you just erase the difference. You can also do this for fairness. Same idea. You have data going in, and you're going to make a decision. This is your primary decision, f theta of x. But now imagine, maybe you say, well, I want to make a decision on something, but it's kind of a sensitive thing. I don't know. I want to make a decision on, am I giving somebody a loan at a certain interest rate or something like that? You can't take into account certain things, like you're not allowed to maybe take into account the race of the person. You're not allowed to take into account maybe age, no age discrimination, things like that. So anything that you're not allowed to discriminate against might actually have some statistical properties that, if you're not careful, somehow propagate into here. Think, for example, of a property like race. You might say, okay, race should not be in here. That's not enough. Because what if you feed in the zip code of where somebody lives that has a strong correlation with race? What if you feed in something else, maybe the school they went to, maybe last name or something? All these things can relate quite closely with race. And so if you're not allowed to use race, it might be that literally everything you have has at least some non-zero correlation with race, so you cannot feed anything in. What are you going to do now? Well, the alternative is to say, well, it has a correlation, but if I can get rid of the correlation, I'm good to go. And so a bunch of neural net processing. At this point here, there's a split. And along this path, you try to predict race. And now you try to ensure that the loss of that second path is really high. So you have a two-player game again. This is a bit like your, well, this is one player, player one. This is player two. And player one is trying to solve the original problem. Player two is trying to ensure that you don't use any information, including any correlations that might be there, not just erasing explicit things, but also correlations need to be erased before you hit on to this path where you make your decision. I'm not saying this is going to work perfectly. I'm not saying it's a certified way to take care of this, but this is one direction that people have been looking where adversarial losses do play a role. And at least it's much more comprehensive than just removing a feature that is literally a feature you don't want, because there could be many other related features that implicitly carry the information. All right, so the last thing I want to cover is GANs and imitation learning. So it's a paper by Jonathan Ho, one of the co-instructors of the class, and it's a paper from 4 years ago now, and it shows actually a very strong relationship between GANs and imitation learning. More specifically, he set up this game. So in GAN, we had discriminator and generator. Now, generator will be our policy, pi, that we're trying to learn. And discriminator will still be d, same thing. And real here will be pi e, policy of the expert. And so we have policy of the expert. A discriminator is trying to distinguish whether a trace that it's seeing came from the expert policy than well from a execution that your learn policy did. If the discriminator cannot distinguish between the expert and your policy, then you've learned to imitate the expert really well, and you're good to go. It's just a GAN objective here. Want to make the discriminator discriminate between the two sources of data, and then Jonathan actually derived it from the energy-based model perspective. And so in his derivation, it already automatically had the entropy in there. Here's what the algorithm looks like. So you sample trajectories from your current policy. This is your current policy. Expert policy is pi e. This is your current policy. Could be a gigantic neural net. Then your discriminator will do some updates based on the loss function for discriminator, trying to distinguish expert traces from generated traces. Then we need to improve our policy, our generator. In this case, policy gradient is used, specifically TRPO policy gradient. And if you look carefully at the objective, let's go back to the previous slide. You look at the objective for the learned policy. The learned policy is appearing here and is appearing here. So 2 places. We want to maximize what it scores. So the first part here, expected value under the policy of log discriminator S, A. This thing over here is your reward, your learned reward for being a state as in taking action A. This thing here is just entropy, which is a canonical thing in RL that you also optimize the entropy of the policies. That's well understood how to do that. So you do TRPO, where your Q function is estimated with rewards that are the log discriminator values. And once you do that, you're optimizing this game objective, and you're good to go. This is then compared with some other methods for imitation learning. Horizontal axis here is the amount of demonstration data required. Vertical axis is level of performance relative to expert. And then ours is from the paper. So this is GAL, Generative Adversarial Imitation Learning. We see that blue GAL actually learns more efficiently, needs less data to imitate the expert than any of the prior works compared with behavioral cloning, let's see, random. Expert in blue is kind of this where you saturate out at the top. And GTAL is a method that was important to compare it at the time, but I don't think people compare as much anymore with now. So now running a GAN to do imitation learning, you can imagine it gives you all the challenges with GANs that we've covered in image generation. And now it's more complicated to find a policy that in turn and through interaction with the environment generates data. Think about it. You think about a pixel CNN. That's like running a policy. You generate 1 pixel at a time, but the only state you generate is your past actions. In reinforced learning type setting, you generate state in the real world that you don't have as much control over. So it's more complex. You're going to have the same struggles though. And so Aravind covered the variational discriminator bottleneck GAN idea. And for imitation learning, it turns out that it is really, really helpful to use this trick. So we covered it earlier. You want the discriminator to not be too powerful, so you let your discriminator work on a latent state. And the objective will introduce noise on that latent state to bring your generated data and real data closer together to get less of a 0-1 discriminator decision and a more gradual decision, which gives you a gradient signal. Here are some results. So mocap on the left, policy on the right. So it's imitating very well, right? It's hard to see the difference between the two. Here's another one for cartwheel. Again, left is the demonstration, right is the learned, and it's very closely matched up. I think this is what Jason called a Chinese dance in the file name. Again, very difficult to see any differences, which means essentially our personal discriminator looking at it can't do it, and at the same time also the discriminator that was trained is not able to do it anymore, or not very well. Here is backflip, again, very closely matched. Here's a comparison with some other imitation learning. So I believe on the right here, we have an implementation of Gale from DeepMind and DeepMind Control Suite, trying to imitate some human motions, including running, but it doesn't look that realistic. And then here, in comparison, you have the variational discriminator bottleneck version, which gives you much better match. You can also do it more quantitatively, looking at the performance here. Lower is better. These are losses. We see in yellow the variational information bottleneck, in blue the original Gale, and we see a lot faster learning thanks to this variation. Any questions about this? Yes, Olivia.
So if stuff that seems to work well compared to behavioral coding, how come it's not like more popular than behavioral coding?
Say it again?
How come it seems like, maybe I'm just wrong, but how come it seems like this method is like less popular than behavioral coding if it comes to work better?
Behavioral cloning is very simple. So behavioral cloning, you just have to learn a policy that goes from input to output. And so you're always going to want to run it at least as a baseline, and sometimes it'll just work already. Something like this is, I would say when you think about what's the difference between, this is a type of imitation learning in the family of inverse reinforcement learning, where you implicitly first recover a reward, in this case the log discriminator, and then from there train a policy on top of that. Often going to reward first is more sample efficient, because often the reward is simpler to learn from data, meaning that less data is required to specify reward compared to specifying a policy. And so often it's more data efficient. And so this kind of sample complexity curves. At the same time, look at compute efficiency. For this, you have like inner outer loops. You're estimating the reward, then you're estimating the policy, and it goes back and forth. So it's more complicated and often also longer running times. And so there's a bit of a trade-off there, where behavioral cloning, you just kind of feed the data through, you have your discriminator trained effectively, and it might or might not work, but if it works, you're all set. Other questions about this? Actually, for the last part, let me just let's see, what's the best way to do this? Actually, let's do this relatively quickly, but just to give you a sense, and we'll post this on Piazza also, of kind of the scope of final projects that we think could be meaningful. So here's one example. Flow++ is a state-of-the-art flow-based generative model. You can explore it to put more pluses behind it by see if you can use FP16 on a V100, use self-attention at different spatial resolutions, scale to larger versions of ImageNet, group convolutions, multi-scale flow training, subscale, block autoaggressive coupling. And you might say, okay, will this work? Well, it's hard to know. I mean, these are the kind of things that you end up doing when you do research in this space. You have some ideas of architectural changes that might actually give an improvement or might not. You'd probably try to think ahead of time which ones you think are promising, which ones not, and start trying them out and see if you get the signal that you're hoping for. Same thing here, pixel VAE, GAN, flow, pixel CNN, and so forth. So we have a whole list of projects that we'll post on Piazza that can give you inspiration. The second list here is all about actually computational bio. So a bunch of projects in Com Bio that we think could be pretty interesting. So we'll post those on Piazza later today. At a high level, things to think about for the final project is that you only have that much time. Definitely, ideally pick something that could lead to a paper, but don't expect that you can actually get a full paper done in the scope of a class project, but pick something where you can do a thorough investigation. So pick something where you can really do some comparisons and try to dig into whether one version of something works better than some other version. So it's not just like one thing you try and that's it. Make sure you can do some comparisons. You have an idea, make sure you have ablations of those ideas, not just the one idea that you're interested in. So having ablations is key, or comparisons. Other thing is, you can look at application domains. There's a lot of application domains where people have not applied unsupervised learning. There was a question earlier, how long does it take to get GAN to work in a new domain? People do it for images, people do it for speech, videos maybe a little bit, but there could be completely different data domains where nobody has studied how to make it to work. You probably need to think very carefully, try a lot of things before you have the right architecture that will make something like that work. So different application domains will be interesting. And then the other part is, if you want to do something that is more on the theory side, that's fine too. It doesn't need to be pure experiments. If you look at some model that is maybe poorly understood and you think you can derive a better understanding of that model, that's totally fine too. It's not just about everything needs to be experimental, though often for a lot of these things, getting clean theory is pretty hard. I would say John's write-up in 2016 that you'll find is probably one of the cleanest things you'll find on GANs. In general, it's just hard. It seems like practitioners push the state of the art much faster than theory is able to keep up, which in some sense gives opportunities, but also I think is some evidence that doing the theory is not very straightforward. And maybe you're running behind anyway when you're doing that compared to somebody who pushes the next experiment out. Maybe let me pause here and see if there's any questions, high-level questions about project scope and directions. Who already knows what their final project is going to be? Curious. I think you know, because we talked about it on the way out last time. So one person knows. Laura kind of knows. So a couple of you know. Well, you still have 5 days, so give it some thought. If you want to brainstorm ideas, make a private post on Piazza. So if you're just kind of thinking about it, you're not sure, just make a private post, and we can look at it. The course team can look at it and try to brainstorm with you, or come to office hours. We can try to brainstorm together. If you can, try to tie it to research that you have. If you work in, I don't know, computer vision, it might make sense to do an unsupervised learning project that involves computer vision. If you work in NLP, try to do something unsupervised NLP. If you work in RL, maybe try a combination of RL and unsupervised learning. Some of these combinations we haven't covered yet. So NLP and unsupervised learning we haven't really covered yet. You can look at last year's offering. There are slides up on last year's website to get a notion of what's happening in that space. Same for unsupervised and RL. We haven't covered it yet. And of course, some things have changed since. But there is a lecture from last year that covers a lot of that junction. There's an application domain that I think is really interesting, which is compression. Again, we haven't covered that yet this year, but you can find it in last year's. And compression is a very direct application of unsupervised learning. We mostly covered lossless compression, where you perfectly reconstruct your data on the output. But it's also very interesting to look at lossy compression, where you look at, okay, what is okay for people? Maybe it's not perfect reconstruction, but when you ask people, is it equally good? Am I equally happy watching this movie or that movie? Yeah, I'm equally happy watching them, even though maybe, I don't know, some things are quite different. If the experience is the same, maybe it's okay. And you can stream it at much lower bit rate by using a lossy compression. I think in compression, there are some benchmarks out there, so you could actually directly benchmark. Same for the bio. Well, the interesting thing about bio is that that's an example of a domain where people have not pushed very hard on what the architecture should be. So it's where you have an opportunity to, a little bit more from scratch, invent what the architectures could be compared to computer vision, where people have been pushing for the last 8 years on neural net architectures for computer vision. But if you had yet another domain, last year somebody did actually databases, and that resulted in a really nice paper. They looked at, can you estimate the cardinality of what will come back from a database query? So you ask, you have multiple tables. In a database query, you'll have some kind of merge of those tables and then filtering. And the order of the merge and the filtering will determine how much compute you have to do. And you can actually do some kind of search over that. But to do that search, you need to know how big each intermediate result will be. How are you going to do it? Well, they did it by essentially training something like a pixel CNN model, autoregressive model, to predict how big the return of a query will be. And then based on that, you can optimize the ordering of your joins and filter operations to do things much more memory efficient and computationally efficient than you can if you use about ordering. So there's definitely application domains that are maybe not exactly what we cover here that is worth thinking about that you might find in your own research. Cool. Well, looking forward to reading the project proposals. It should be a lot of fun, and see you next week.